right, good morning, or good evening, I should say. Um, I usually make videos in the mornings, but this is an exception. Okay, so here we are. I'd like to make a video on the following topic. In fact, this is probably going to be one of two, maybe three videos, part one, part two, part three kind of thing, because the idea or the objective here is pretty deep. Anyway, so what I wanted to do is make a video on proven trig identities. Now, typically, whenever I've taught either pre-calc, honors, or regular pre-calc, I always spend some time on these topics. And it's hit or miss with some students. Some students really like it a lot. Some students, kind of don't see the point of it. Um, Now, through my personal experience when I was learning these things back in high school, this was by far my favorite topic of probably the whole year, but possibly definitely within the trigonometry, because trigonometry, even though it's really really important, but it could be pretty dry, especially if you're like doing like right angle trig. You're like basically finding angles, sides, and things like that. It's very mechanical. There's not a whole lot of thought process to it. However, proven identities, that really is it's a really good intellectual exercise as opposed to just a mechanical exercise. Anyway, uh, okay, so that's really the goal, to introduce, and in this particular video, it'll probably be part one of maybe, well, at least two, maybe three, depends on how deep I want to take this. And the goal of this one was introduce what identities are and some of the simpler, the basic techniques in this. It can get a little more challenging, but that's actually why personally I like it, because there you have to kind of, well, it becomes more like an intellectual puzzle. Anyway, so let me clear this. Now, who is my target audience for this particular video? Normally, this topic is introduced in pre-calc, so I'm actually, so it's pre-calc, calc, class, either honors or regular, either one of them, but primarily in the honors. That's what I would kind of would think that really belongs. However, what makes this unique, this particular video, is that I'm actually making this primarily for my Algebra 2 classes. Um, and even though they have not had trigonometry yet, and yet it feels like I'm jumping way, way deep into the trigonometry by doing the topic called proven identities, even though they have not had trig. So this is going to be a little unique, but I think it's still okay. Uh, for the benefit of the people who have had this before, I've had trigonometry. Some of the early parts of this video will feel like it's a review, but that's not bad. It's not a bad thing to review things before you get into this particular topic. Anyway, so I'm going to start. So this really is kind of to targeted towards my Algebra 2 class or classes. All right, so let's actually talk about what is an identity. An identity is basically any equation that is always true. That's a fact. So meaning as simple as, well, like 10 equals 10. Is that an identity? Yeah, it's an equation. It's an equal sign. Left side equals to right side when, always. So you could say this is an identity. That's a very trivial identity. Really, actually it's like a reflexive property. And if you remember those things from the early parts of algebra. Anyway, so another identity. What about like 5x equals 5x? Well, again, that's always true, and now we have a variable in here, but that's always true as well, because no matter what value of x in here and value in here, it will be the same thing. So this is kind of a trivial thing. However, not all equations are identities. As an example, if I give you this, 10x equals 20. Is that a true statement? Well, it depends. If x equals 2, then yes, this is true. But so this is what we know as, it is an identity, but it's conditional identity. It's conditional because under a certain condition, if x equals 2, then yes, this is true. Otherwise, this is not true. So this is not what we're really studying today. This is not, we're not looking for conditional identities. We're looking for identities for all variables, for all values of variable. Anyway, the format of it could be kind of very simple or it could be very complicated. I'll give you an example in a second what I mean by that. Uh, the variables that we're gonna use here are either letter x throughout the whole thing, or typically theta, which is a Greek letter, theta. That's how it's pronounced, theta. It's a Greek letter theta, really representing angles. However, either one of them is acceptable. Okay. In fact, if you were going further into calc, very often we use letter T for which stands for time, some kind of time measurement. So we have as a common variable in calc, we use letter T in with trigonometric or any kind of equations. Anyway, so let me give you an example what this is going to look like. It can look as simple as, oh, sorry, right. So here we go. I think it's on the next slide. So here is a couple of, just basically a screenshot of some college textbook, or college or pre-calc, I don't remember which particular book this is. Samples of what were the instructions here, like prove this, that this is an identity. Prove or disprove, maybe. I don't know, this particular. So prove or verify. Sometimes it's called verify. It depends on the particular book. Verify the following identities. So the idea here is you're being told that the left side equals the right side. So if this said prove the following, you're being told that this does equal to this, and you have to show the steps. You kind of demonstrate why they are equal to each other by basically focusing usually on one side, or one of the sides here, and just kind of rewriting it, manipulating it, and making it look like the other side. Now in this case, I just glancing at this. This is a really, really simple, there would be a very simple solution to that. However, right now, I mean, the goal is really not, I'm just introducing what identity is. So some of them are, a couple of one or two steps, but some of them take maybe a lot longer. Here's an example of something a little more complicated. We're definitely not going to get to this in one video, or even maybe second video. Maybe a second video would probably get to that. Yeah, this looks like not really that difficult. Okay. Anyway, so that kind of introduces the idea of what an identity is, and we'll talk about what are the rules of proving or verifying identities. The idea, if you have two sides, you have left side equals right side, and either the question is yes, you know that this is a fact, you have to show the steps, or you're saying, well, prove whether this is or not an identity. So that, I'll put a question mark here. The idea here is this is not solving an equation like in a typical algebra 1, algebra 2, or even pre-calculus. You can do when I have my goal is solve an equation, right? Then I'm doing something to the left side and something to the right side. As an example, if I have 3x plus 4 squared minus 8 equals 15, as just rough example, don't know, don't care what this is going to look like. um, in fact, let me put a I don't know, 17 here to make it like actually doable. So if I put 17, I could see that. Yeah, and your first step would be like, oh, I'm gonna add 8 to both sides, and I'm gonna take a square root of both sides. Well, with identities, you're not allowed to do that. You're not allowed to do something to one side and something to the other side at the same time. Like here, the obvious step is plus 8 plus 8. But you can't do it with identities. You basically pick a side, left side or right side, and we typically pick the more difficult, the more challenging looking side. As an example, on the previous one, well, actually, this looks complicated. So this may not be the best examples. However, let's say if this was like this, and this was equals to 1. Yeah, of course, this is going to be a more complicated side. I'm going to pick on this side, and try to manipulate it to make it look like the other side. But you're not allowed to manipulate both sides at the same time. You pick a side and you work on that. Um, okay, and you'll see what within a couple of slides. You'll see exactly what I'm talking about. So let me clear this out. So the rules are: you're working only one side at a time, and as a strategy, you're typically working on the more difficult side. And there's a couple more strategies. Basically, when you look at it, when you're seeing certain kinds of things, your mind should go, oh, this is probably, it's going to require this technique or that technique. And this is what one of the things I love about identity work or solving identities, because you really don't know for a fact. It's like a maze. When you have a maze, you start off, something over here. You start off, this is your exit, and this is your entrance. And you really don't know where to go, which way to go. Sometimes you'll hit a dead end, and you have to back up and maybe try a different way. And hopefully, if you see it ahead of time, maybe you will see how you get to the other side. But it might require more than one restart because you might be hitting dead ends. Um, all right, so those are some preliminaries. Here we go. So let's actually start. So I'm going to skip this. We're not ready to do any of this yet. So because in huge part because this is going to be addressed to my Algebra 2 classes, that has not had any trigonometry yet, not officially anyway. I think I made a one or two where I had you guys watch one or two trigonometric tutorial videos just to introduce it, but I don't really expect for you to remember all of it. And it definitely not what you watched and in the basic right angle trig type of videos. You're not going to be able to use those skills, not yet anyway, to prove trigonometric identities. However, I'm going to treat this, it doesn't matter, I'm going to treat this that basically as things, like trigonometric, what are trigonometric things that I'm going to manipulate, and I'm going to prove things with just those things. Now, what are the things? Well, in trigonometry, and again, this is real for those of you who already have had this. This is just a review. We basically have two major things. One, so this is sine of x or letter theta, whatever letter. Uh, so this is an operation, or sometimes called ratio. If you're talking about right angle trig, then you're talking about if this is my x as the angle, sine of x means something like it's basically the relationship between the measurements of the opposite side and the hypotenuse and so forth. I'm not going to get into that right now at all. I'm just going to say sine of this is a thing. Now, in the haste of things, and I'm kind of gonna forewarning you that I'm technically gonna commit sort of like a mathematical grammatical mistake. I'm very often just gonna write the word sine without the letter x. We know for a fact that this by itself is improper. You need to, like, sine is an operation or it's a function, but you can say operation on something, like on something here. However, in proven identities work, very often I just neglect that for out of convenience. But yeah, please understand that the sign by itself does not exist. Sign of something. It's very similar to if I said, for my my algebra 2 class, if I said ln of something, right? Ln of what? You can't just say ln by itself. Ln of 374 as an example. Well, that makes sense now because that you could put in the calculator to get a value, or even if you don't just make a like of this, that makes sense. Whereas technically speaking, this does not make sense. But again, this is really for the quickness of it. I'm just going to write the word sine, right? Sine instead of sine of theta. I'm just going to write sine of that. Now that's the number one, what kind of most important thing. The second important thing is cosine of, again, of letter x or theta or some other variable, but quite often I'm going to neglect it. I'm not going to list that. Oh, by the way, like it's pronounced sign because the actual word, the actual, that's sign. However, it's being abbreviated by three letters, so it looks like sin, but it's pronounced like sign. Please don't pronounce it as sin, okay? Because it'll give away that you really don't know what you're that you were just a beginner, okay? And this is pronounced cosine, not cos. Although very often I'm not, it's just almost as a joke. I'll say cos. Like I mean, it's just literally it's almost like a mathematical joke. Okay. Anyway, this is cosine, cosine of something. So those are the things like there are fundamental things. Now I'm going to erase this part. Now here from this we can build other things. And so number three is what's known as tangent. It's pronounced tangent, so tangent. And again, it's tangent of something, either variable theta or x or t, whatever the variable is. I'm going to neglect that almost by design, by just kind of introduce it right away. That's I'm going to be manipulating tangent. Okay, not the letter x. I don't manipulate letter x. I manipulate tangent. However, technically speaking, this is incorrect, to write it like that. Anyway, so what is tangent? Well, from the right angle trig, we know that as opposite side, or measurement of opposite side divided by adjacent side. If this is my theta, ADJ. Especially in geometry course where trigonometry is first introduced, maybe that what this. But however, the more important definition, we're not dealing with triangles. We're dealing with a function, okay? And tangent is defined, not defined. It's just the result of sort of what sine and cosine is. Tangent is really a ratio of sine divided by cosine. So if you know the sine value and you know cosine value, you automatically know tangent value. You just divide them into each other. But more importantly for us will be the strategy of turning everything into sines and cosines. So if I have an expression as an example back here, like an expression of a bunch of stuff in tangents, or well, actually I don't, I actually, yeah, like right here, like cotangent, you'll see these other things. The strategy might be, well, turn everything into sines and cosines. They're the fundamental things. They're like the basic things. And then maybe I can manipulate and cancel and simplify and so forth. Okay. So that's this. Now there are three other things. In total, there are six trigonometric things. So the second thing, or was three, four, number four is, well, what's known as, if I flip sine, in other words, put 1 divided by sine like this, it gives rise to this brand new function. We're going to call it cosecant. It's abbreviated, again, with the letter x here and so forth, but it's abbreviated to be CSC, but it's pronounced cosecant. And you'll see why in a second. The word, secant secant has to do with cosine. Okay. So that's that. That's basically 1 divided by sine. Well, that also means that sine, all of a sudden, when I introduce this, I introduce this, if I flip this, I'm going to get this. Sine is 1 divided by cosecant. Okay. So we'll use this kind of heavily back and forth. Okay. So, all right, that's that. Now let's do number 5. So this is 5. Now I'm introducing secant. Secant, it's pronounced secant like this. It's abbreviated sec, SEC. And what that is just 1 divided by cosine. If I flip, if I do reciprocal of cosine of x, but cosine, I'm going to get secant. All I'm doing is I'm introducing a new way of thinking about cosine. Okay, so they are definitely related to each other. And lastly, and you can obviously guess by extension, Thing number six is if I take and reciprocate tangent. In other words, 1 divided by tangent of x will be, and what this is known as cotangent, abbreviated cot, C-O-T, but it's pronounced cotangent. From again, from the word tangent here, it's a co. The word, the prefix co, just kind of put it like cosine, cosecant, cotangent, right? Like followed by this is tangent. Tangent. Okay, misspelled. Okay, that's, I could ignore that. So right from here, though, we're almost immediately introducing a whole bunch of different ways of thinking about it. So what's cotangent? Well, if cotangent's 1 divided by tangent, that's the same, basically saying I'm going to flip this fraction right here. I'm literally just going to reciprocate like 1 divided by sine divided by cosine. Well, if you know through your middle school algebra or pre-algebra, when you divide by a fraction, same thing as multiplying by the reciprocal. It's upside down. So this really becomes cosine divided by sine. And what one of the sort of the quicker you learn these things, the easier this, and not only easier, but in fact I would say more enjoyable this whole topic will be. Uh, that if you know like sine and cosine and what tangent is and how they're related to cosecant, secant, and here's cotangent, that they are reciprocals of each other, and what is the relationship between all six of these. Uh, the only direct relationship that is not obvious is the sine and cosine. Not yet, anyway. At after the first lesson, maybe the second lesson, when we get into Pythagorean identities, sine and cosine kind of like they're great together. But meanwhile, I can't really mix them. I can mix sine and cosecant and so forth. Anyway, so as a immediate byproduct of this, like pretty much like on the spot, when I say, well, what is sine times cosecant? Basically, it's reciprocal. Well, it's automatically 1. Because remember, it's sine is sine, and cosecant is 1 divided by sine. So if I have sine times 1 divided by sine, automatically they cancel. It becomes 1 times 1 is 1, right? So anything divided by its own reciprocal, and that applies not only to trig, but just in general. Like here, 17 times 1 divided by 17 equals 1. Okay, it's its own reciprocal. Remember, 17, like 17 over 1. Um, and so that extends further to the other functions. So as an example, cosine times secant is automatically 1 because they are reciprocal of each other. And by you can go one more step, tangent times cotangent equals 1. Okay, so that's sort of like the quicker you get to these like simple things, the easier this whole thing will be. And I'm hoping that you would actually enjoy this very much, like the way I tend to enjoy uh, proven identities, because they can look really really difficult, but if you break them down, if you have some algebra skills, it's fun. Anyway, so right from here, we'll just extend it one more as an example. What if I have like I don't know, 3 of them multiplied to each other? In fact, I think later on there will be a problem like this, but I'm coming off of this off my head, top of my head. Well, secant of x, but I'm just being kind of lazy. Secant times cosine. Oh no, that's too easy because we already know that's a 1. So secant times sine times cotangent. I don't know, just off the top of my head. So let's see what this leads us. Well, one of the strategies will be, like right now it's not obvious. One of the strategies will be, hey, if nothing's obvious, let's turn everything, especially if I have these other the 3 the not major ones. Let's turn everything to sines and cosines. So what is secant? Well, secant is 1 divided by cosine. Okay. Now sines that typically I don't, like the strategy is leave sines alone, leave cosines alone. Don't turn them into like yes, you can turn it into theoretically 1 over cosecant, but that's not going to help most of the time. The goal is turn everything into more familiar sines and cosines, and then maybe cancel and so forth. So I'm going to leave sine alone. Now, what's cotangent? Well, cotangent is cosine divided by sine. And I want, like I don't want to say obvious, but it is obvious with a little bit of, learning. So for the pre-calc kids who are watching this, this is like, oh, that's obvious. But for algebra 2, you've never seen this before. This is not obvious. Well, look what happens here. So on this side, when I say on this side, theoretically, this could have been like, right now I'm just having an expression here. I'm saying just let's simplify it. But theoretically, this could have been like an identity. Prove it. Prove that this is correct. Notice I'm picking on the difficult side. Now I'm not starting on side that's simple 1, because, well, how do I express 1 different ways? There's infinitely many ways I could express 1. Sine divided by sine. Yeah, but I don't know if that's going to help me, to solve this. So you pick on the side you start working on the side that there's more stuff to do with. Anyway, so what happens here? And hopefully you're seeing it. Like sine and sine cancel. What else? Cosine and cosine cancel. And leaving you with what on this side? 1. Right? Everything canceled away. And the other side was 1 the whole time. You kind of like, I don't bother writing it each time 1, 1, 1, but eventually just going to bring it down and say, oh, so is this an identity? Yeah, and I just proved it. That secant of any angle, whatever the input is, secant times sine times cotangent, which is kind of like, well, what the heck is this? Yeah, but that all boils down after simplification equals to 1. So yes, this is an identity. So there I just kind of introduced and already proved the first, example. Like if this started off with that. Now, on the other hand, if my original problem was not this, but let's say if it was, oh, the other side was cosine, just prove that this is correct. Well, I just proved that it's not correct. That according to this, if the other side was cosine, no, it would be a false statement because there's no way. Well, actually, I shouldn't say there's no way. Under certain circumstances, 1 equals cosine of x. Yeah, under certain x's, this is true. Right? Again, for the trig people, like, oh, of course I know that this is true sometimes for certain angles, for what, pi over 2 and multiples of it. Well, I should say odd multiples of it. Okay. But otherwise, what am I saying? I've been thinking, no, for 0 and 180, right. Sorry, that was stupid of me, right? Like in this case, x would be 0, pi, then 2 pi, basically multiples of pi, okay, and so on. In fact, infinitely many answers, unless you say, oh, I just want the domain to be from 0 to 2 pi. Anyway, for those of you who didn't follow me, that's okay. The point is, this is not, like if I had the word cosine here, this would not be an identity because, like it would be like 1 equals 1. Meanwhile, if I had not 1 but something else here, it would be a false statement. Okay. All right. Let's see if there's anything left to talk about things. Things. Right now, again, you may not even know what sine is or cosine is. It doesn't matter. Now, one thing before I walk away into the next example, and see, yeah, the next. Oh, okay, yeah, next example. Yeah, one other thing I want to mention is about notation about certain things. As an example, sine of x, and I'm being neglectful, times sine of x. The x's themselves don't multiply. It's not, it's what this really is sine of x, some value squared. But notation wise, it's a simpler way of writing sine squared of x. So make sure you understand this. This square does not apply to letter x unless you wanted to apply. In that case, that would be sine of x squared. Oh, that was a bad. Let me sine of x to the second power. So in that case, what you're doing is you're squaring the x first, and then you say, well, whatever value this is, I'm going to take sine of that value or of that function. Meanwhile, this is not the same thing. So this is from notation perspective, when I say sine of some exponent goes up here of letter x. And we typically, especially in the early part of trig, early part of proven identity, it's always going to be a 2 here. If nothing's written there, it's a simple 1, right? It's just like regular exponents. If there's no exponent, it's invisible 1. Okay. All right. So I just want to emphasize so that I'll be like, oh, what the heck is this? This is not the same as sine of x squared. They're not the same. Okay. All right. So let's clear this out. I'll go to the next slide. All right. So you must know the 6 very basic things, and I'm going to list them out one more time. And depends on who if you've already if you're if you've had trigonometry, depends on your teacher how they list this out. I typically list them out, and I want my students to kind of make this association. I write sine of x or theta. I'm just going to be neglectful. Cosine. I'm going to put this in a column form. You'll see why in a second. Tangent, cotangent, secant, and cosecant. So you could kind of practice pronouncing it this way: sine, cosine, tangent, cotangent, secant, cosecant, and just kind of back and forth, not back and forth, just kind of forward. However, the reason why I write this like this instead of maybe in a row format is now I can make this really convenient association. The 2 outside, and as you work your way in, they pair up in a special way. And lastly, I'll do this one. Yeah. Okay. They pair up in a reciprocal way. In other words, tangent is a reciprocal of cotangent and vice versa. Cotangent is reciprocal of tangent. In other words, like this, the tangent is 1 over cotangent. And cotangent is 1 over tangent. But what's also nice about the, seeing them like that, the product of these two, of the pair of each one is equal to 1. Sine times cosecant equals to 1. And, I don't want to say you could see it this way, but that's the association because they are reciprocals of each other. Now, on the other hand, if I say what's sine times tangent, um, actually, well, you can do that. Well, what's sine? It's sine times sine over cosine. Now, in this case, nothing really simplifies, doesn't cancel. In fact, it kind of complicates to become sine squared divided by cosine. Now, in this case, this actually looks more complicated than the original part. If I say this is my original, this looks more complicated. But in this case, it was about the skill of it, right? Just like I could do this from understanding that this was. But other times, I might have this, and I might say, well, wait a second, I could see that this is really like if I separate sine away from this, like into this is tangent. So you should be able, because it's an equation, you should be able to go back and forth. All right, so let me erase this. So that was not a really necessarily good, um, instructive thing. However, what if I have sine times cotangent? Well, sine is sine, so just kind of leave sine alone. Sine times, well, what's cotangent? Well, that's a what? Cosine divided by sine. And then you can say, well, wait a second, that simplifies to become cosine. And there it is. So that's this part. So this could be an early, yes, it is an early part of an identity, prove an identity. They could give you prove the following: sine times cotangent equals cosine, which looks kind of like, whoa, what is this about? Like even if you don't understand trigonometry, if you don't really haven't been exposed to, you don't know what sine is, as long as you follow these quote unquote these these rules that apply to these things, you're like, oh, I can do this. Sine and just replace what cotangent is and simplify it, and you proved it. You got it. Okay. Um, Let me see if there's anything else. Oh, one other thing I want to say before we actually kind of do more examples. But so once in a while, I mean, I shouldn't say once in a while. I mean, like as an example, like cosine divided by sine of x. Well, for those of you who know um, that what this really can represent, the value of this can be zero, right? Like, and we say, oh, you're not allowed to divide by zero. And the way we get away from that, we get away with it, we're basically saying that's fine. We're not allowed to divide by zero. We just assume that all of this works in the domain that it's allowed to work in. In other words, in this case, I would be saying, oh, x is not allowed to be zero, because for those of you who know trigonometry a little bit, sine of zero is zero. But it would work for other things aside from this. So we kind of just basically not close our eyes on it, but just say, well, we don't have to worry about it. We're just going to limit this only to the domain where it does work. And so if this is in case some of you are like are pretty thoughtful about this and say, wait a second, what I know you're not allowed to divide by zero, but what if x equals zero? Yeah, that's a really excellent insight. But all of this works in its own domain, and it takes a little bit more than just what I just it felt like I'm just doing. The explanation feels very surface like, but it works. The explanation was a valid explanation. Anyway, let's move on to one or two examples. So let me clear. Do I need to clear this? No, it doesn't matter. So here we go. Okay. All right. This is just a restatement, right? Like a restatement of these same things. Okay. And the quicker you become familiar with it, the better off you are, right? It just becomes a much more enjoyable instead of. So here the idea is like if you have to do these kinds of problems and you have to pull out a 3x5 card, so look back to your notes, you're not going to enjoy it. It's going to slow you down. It's going to feel tedious. It's going to suck. But if you know this by heart, and almost through not intuition, it's obviously it's not intuitive that what a sign is. You just like accept it, like it's a thing right now. If you haven't had trig yet, but the idea here is, all right. Well, let's simplify it. Let's turn this into a proven identity. I'm just going to say, what if this side equals to one? Is that a true statement? And like prove this or disprove it. Well, it's an equation now. So what's cosine? Now, cosine is cosine. I like cosine. I mean, we typically don't want to mess with cosines or sines, but cosecant we want to get rid of. So this really becomes cosine times, well, what's cosecant? Well, 1 over sine and equals, and I'm not going to write it each time 1. I'm just going to work my way down in the column fashion. So what is this? Well, what's cosine times sine? Oh, that is cotangent, right? Co yeah, like it's just you just, and does cotangent equals to 1? Well, it can under conditions, under certain circumstances. Yeah, for pi over 4 as an example, it would work. If I put a angle in here, specific value in for this letter x, it could work for if I was solving an equation. Yes, x could be pi over 4 and a variation of it. Okay. Um, I guess pi over 4, so the next one would be what, like 5 pi over 4 as an example, and so on. But that's not the point, right? The goal here is really don't, even if I don't understand it, hey, cotangent of x equals to 1. No, that's the false statement. So you say this is not an identity. So this is not an identity. Now, if the original problem, on the other hand, if over here instead of 1, I literally had cotangent, and you do this operation, you say, well, the other side is cotangent. Oh yeah, it is a, yes, I just proved it. Cotangent equals cotangent, of course. Okay. Um, okay. And so, I mean, this is a, obviously it's a really, really simple example. It's a beginner example, but, it's based on, your conference is based on being able to do these things pretty quickly. We can move on to something a little more complicated or something actually more fun. Okay, let's do one more. So right now it's not even an identity. It's just like, hey, let's manipulate this side. Okay, let's do it. So what am I looking at here? Well, there's a couple of ways of looking at it. I'm going to change the secant into, it's what it is in terms of sines and cosines, 1 over cosine. I'm going to turn, so you could write this as sine times, well, see, this is 1 over cosine, kind of like this, and this is sine over cosine, right? Like I just turned them into sines and cosines. Now, over here, you could say, well, wait, I can see that. This is going to be 1. Well, hopefully you're seeing this, because what is this right here? This is sine divided by cosine, right? This, if all I had was just this numerator, that's what it would be. And this is being divided by sine divided by cosine. Now, which I know that this is tangent, right? Like this is tangent and this is tangent, but frankly, I don't even need to reconfigure this to look like tangent. Anything divided by itself equals to 1. So if the other side was equal to 1, I'd be like, oh, I just proved it. But let's see where this can go. I mean, another way of this is it. This is pretty important. So I have my numerator here is this. I'm going to write it sine divided by cosine. That's my numerator. But remember from your middle school years, or when you divide by fractions, the same thing, the equivalent of multiplying by the reciprocal of this. You're dividing by this, right? You're dividing, that's my denominator. You divide, normally it would be divide by here. But another way, if I can say, well, I'm going to multiply by its reciprocal, change the cosine and sine position. So I'm multiplying by this. And of course you could see, hopefully you could see that, oh, they cancel. Sines cancel and cosines cancel, leaving you with 1 divided by 1, right? So which we already knew just by looking at this, anything divided by itself is 1. Okay. But it isn't important. You will see this comes up all the time. This is what's known as complex fraction, where you have a fraction divided by another fraction. As an example, in your middle school, you might have had like 5 over 7 divided by, I don't know, 10 over 21 as an example. And just not really random, and it's sort of random, but I can, like I saw, I set this up to simplify. So you can think of that as, well, this is really 5 over 7 multiplied by the reciprocal of this. The reciprocal. And the reciprocal would be 21 over 10 in the denominator. And then you carry through the operations, normal way. Like, all right, 10 and 5, they partially cancel. That becomes a 1, that becomes a 2. And then 21 and 7, okay, that's 1, and this is 3. So the answer there, simplified, is 3 over 2. Well, in trig, we're not going to necessarily get numeric values unless it just simplifies to 1, or something very, like equivalent to 1. Um, but typically, like we're looking to simplify by multiply by the reciprocal. If I have a complex fraction, like this is a complex fraction, fraction within a fraction. Um, anyway, so this right here was really had nothing to do with trig. It had to do with just a skill of simplifying a complex fraction. Okay. All right. So let's see if there's any. Um, let's see if there's any more easy ones. Like, did I set them up? Okay. All right. So the question here is, and this looks, actually I don't know to you whether it looks difficult or not difficult, but it looks kind of easy. Okay. So the idea here, the skill here is like I'm going to change things. I don't like cotangent. I don't like secant. I'm going to change everything to sines and cosines. Okay. So the other side, clearly, I'm going to leave this alone because this is a less complicated. This is a more complicated. There's more stuff I could do here as opposed to here. So I'm going to rewrite everything in sines and cosines. Well, what's cotangent? Well, that is cosine divided by sine. And the quicker you know this, the better. Times, well, what's secant? Well, 1 over cosine. Okay. Now, sine squared, I could write either like, leave like, yeah, in fact I will. Or you could literally write sine times sine, right? Like that's what sine squared is. But I'm gonna list it out like just the way it is because I'm okay with being squared. I'm not gonna bother with letter X. And the other side is sine, which I'm not gonna rewrite because this will just simply drop, and we'll decide in a second whether that's true or not. And hopefully you're already seeing it because I already see it. Well, what happens here? The simplification is cosines go away. They cancel. And I have a sine squared and a sine in denominator. Well, this is going to cancel with one of these, leaving you with just sine on left-hand side. And on the right-hand side, there was a sine the whole time. It just dropped down, sine of x. And at this point, I will put x as only for sort of mathematical grammar. And now I decide, of course, that's true. Yeah, it's always true. Okay, sine equals sine. So yes, would be a yes. And there is my sort of introduction to it. But yeah, so even if you don't understand, if you don't know what sine and cosine is, if you've never, it's just I might as well use like symbols because that, like oh okay, star equals 1 divided by happy face. I don't know. It really doesn't matter. I mean, what I'm doing is I'm manipulating symbols when I do identities work. Now, obviously, there's more. Like this could be meaningless, but we know that sine and cosine, they actually mean something in trigonometry. But for the purposes of proven identities, it doesn't matter what they are, right? Like it's like all I care about is the relationship between them. Okay. All right. I think I'll. Well, let me see if there's, what's the next slide? Okay. So the next video, because I think this video is probably going to get, well, yeah, it's definitely going to get too long for, is it? Uh, um, I'm gonna introduce. You know what? I'm gonna push the limit. I'm gonna overlap. I'm gonna do introduce what these guys are in Pythagorean identities, but then I'm not actually gonna work with them. So the Pythagorean identities, it's really based on Pythagorean theorem, right? So what's Pythagorean theorem? It's like when we had a triangle, you know, and we're gonna call this A, B. It doesn't matter which one's which, and we're gonna call this letter C. But C is always reserved for the hypotenuse. Remember that's always the case. So we always say, oh, the Pythagorean theorem is A squared plus B squared equals C squared. And we typically use that to solve for one of the variables for A or B. In this case, we're not going to actually solve for the we're not going to get the plus minus square root of, if I wanted to solve for A as an example, I would really do C squared minus B squared and square root it and do the plus minus business, right? Like we'll never have to actually solve for one of the sides, one of the variables. Uh, it just it not only looks like Pythagorean theorem, it really is Pythagorean theorem when it applies to unit circle. Now, unit circle, for those of you who have had it, like, all right, more or less understand it. Maybe you do understand, maybe you don't. But if you've never had trig, obviously you don't know what a unit circle is. You don't know what the heck I'm talking about here. But that's okay. All again, it's a building of like relationships of these things. They are, as far as we're concerned, they're just things. And the things will be like this. Here's the relationship. Sine squared of, I'm going to call it be official here with letter x, plus cosine squared equals, cos of x equals to 1. Okay, and where did that come from? That's a lesson in itself, right? Like I'm not going to, compound this lesson with that. Um, that's an important in fact it's a hugely important relationship. It's one of the most important in trig. No matter what the angle is, right, like inside here, no matter what the angle is, could be like 0.00001 degree, but okay, and this will work uh, for that triangle. And even when we get away from triangles, this still works. But what's nice about this, and I'm going to just kind of introduce this a little bit, is, well, one, number one, like, and this is a big one for me. Like in my classes, when I give very often, especially at the beginning of the lesson, I'll give a number and say, write, find 10 ways of writing this number or an expression, right? Like especially using logarithms, like doing all kinds of weird things. Uh, like what is one? Well, one, it could be like you've written 5 divided by 5. Okay, that's sort of trivial. That's nice. That is absolutely true. You could also write it. Well, I'm gonna write it. Okay, that's ln of e. Well, like that's also pretty nice. That ln of e is 1. Yeah, like that's a really, really fancy way of writing 1. Well, guess what? You just learned a brand new way, even fancier than this. What is 1? 1 is sine squared of any angle plus cosine squared of the same angle equals 1. That's a pretty fancy way of writing 1. And where it comes in handy, there's lots of examples. We'll go through, in the next video and in person and so forth. Okay. Um, let me stay on this for a second or a minute, and I'm not going to develop any more. This is like This is the number one, the biggest, Pythagorean identity. There's two more, which I'm not going to get into in this lesson. But what's nice about this, besides the fact that it can lead to other um, identities, well, right from here, if I solve for one of the variables, as an example, not one of the not letter x, but like let's say what is this? Ah, wait a second, that's 1 minus sine squared. I just like rearranged that. That's pretty important because there will be times when I want to convert everything to either just to sines or just to cosines, and maybe or find some kind of simplification then. Normally, if I have sine without the second power, I have no idea. I'm stuck. Like there's nothing I can do here. I'm done. Right? Like there isn't anything. But the moment I have a square on both of them, so we love squares. Oh, that's a 1. That will simplify. Okay. So in its own right, it's a really great Pythagorean identity, but it also leads to other identities. So what about this? What about what's sine squared? Well, it's 1 minus cosine squared. And that's nice, but I'm going to take it one more step on both of these. On the, well, hopefully you're seeing this using your algebra skills, right? Like at a certain point, this really becomes a test of your algebra skills, like how how many different things you could put together. I'm going to erase this because I don't think we need this anymore. Well, this if I use this property just from simple, a minus b, a plus b. Look at that. This cosine squared could be thought of as factored form of 1 minus sine, 1 plus sine. Look at that. How do I see that? Well, I see that as 1 is like 1 squared. So it's the difference of squares. Difference of squares. They are, and they leads to multiplication of two conjugates. Now, by the same logic, by the same skill, what is this? This is 1 minus cosine times 1 plus cosine. Look at that. All of a sudden, I could go from squares, which normally, if I have a sine squared by itself, I mean, it's not like I can't do anything with it, but technically, well, technically I could do this. This is exactly what I could do here. But normally I'm like, what do I do here? Unless I divide by sine, I leave this alone. Meanwhile, you could bring the powers down to this, and along the way there will be examples. And in fact, maybe I'll go back to the original, like way back. Like I don't see anything here outright, but I see things like this. I like that. These two are conjugates of each other, right? They are conjugates. Uh, Let me see if there's. I don't spot any immediate conjugates right now, but that's a conjugate. When if I were to, in fact, I could say that's exactly how you would do that problem. You would find a common denominator, which you would find, you would multiply them, and they would become a conjugate, and so blah blah blah. Okay, all right. Let me. I will undo that in this case, because we're definitely nowhere near ready for these problems, not yet. Okay. All right. I think I'll stop here because this video will be very long if I don't stop. Okay. So yeah, we just started on Pythagorean identities, and I'll pick up the second video pretty much probably from this slide, and yeah. Okay, and I will see you in the next video and or in class. Okay, good night. Let's do that. And we could, yeah. All right, so we're up almost a full hour. By the way, everything we just did today, or just in this lesson, obviously you could pause and rewind and try to work ahead of me, or just kind of really solidify. But this really would take probably three or four lessons in class with definitely a little more interaction between each example, but time wise, this would be a really thorough introduction. Okay, all right. Well, good night again.